And the first question, what was for me, not what I can do, but what the customer needs, because I have a lot of requests from our salespeople and from our customers. Is our software can make analysis of rheological data and predict viscosity? And now we can say yes, we can. So today I would like to tell you about a new feature in Kinetics Neo software, especially for rheology. Here. Yeah, there will be 3 points. First, about rheological measurements, especially for kinetic analysis. And we speak about curing reactions, curing and cross-linking. The curing and cross-linking, there are the reactions which happens during the using of paints or adhesives. A second part is preparing data for kinetic analysis, and the last one is some kind of application examples. Here, general theoretical background. If you have some material, for example, amorphous material, then we can put it into oscillating rheometer, make heating, and measure viscosity. And in this case, we can measure viscosity at different temperature. And we can see that the viscosity at low temperature is not the same as the viscosity at high temperature. So at low temperature, material is hard or high viscous. If we go to hot state, to high temperatures, then material is liquid and it has very low viscosity. So here we have decreasing dependence of viscosity on temperature. There are a lot of models which shows descriptions of viscosity on temperature, and in Kinetics Neo software we use Arrhenius dependence, where viscosity has exponential dependence on inverse temperature. So this happens if no any chemical reaction inside. But if you have a chemical reaction, then actually we have two materials. One is a reactant before chemical reaction, and a second one is a product. It is after chemical reaction. Here you see the viscosity, how it depends on temperature for reactant and for product. But if you measure material which has a chemical reaction from reactant to product, then the curve looks like this. Firstly, it goes on a reactant curve, then it has a jump from reactant to product during the chemical reaction, during curing or cross-linking, and then it goes on the product baseline. If you want to see only chemical part of this curve, then we take two values. A first value is the difference between current state and reactant baseline, and the second one is the difference between a reactant and product. If we calculate a ratio between them, it's called alpha, and this value changed from 0 to 1, and it shows that at the beginning conversion equal to 0, reaction is still not started, and at the end conversion is equal to 1, here reaction is already finished. So conversion shows us the chemical part of our measured state. And now what is necessary for kinetic analysis? It's the same like for TSC or TG. We need several measurements which are done at different temperature conditions. For example, here we have 3 curves which are done for low heating rate, it's slow heating, fast heating, and medium heating. All curves have the common initial part. It's a baseline of reactant, where reaction is still not started. It has a common final part. It's a product where reaction is already finished. And they have a different medium part where reaction goes on. How it works generally in Kinetics Neo? Firstly, we have measured data from our rheological instrument. Then, for example, here for curves, then we put them in our Kinetics Neo and make data import and processing, just to remove a baseline and recalculate to degree of curing. Then we create one kinetic model for all this experimental data. So if we have one kinetic model, for example, autocatalytic model, and we know that this model works for any temperature and for any heating rate, then we can use this model for simulation. We can make predictions for isothermal conditions, dynamic conditions, or some arbitrary conditions. We can make predictions of different types of signals. For example, what is degree of cure, what is the curing rate, what is the viscosity, and of course we can make optimization of curing profile. And now we have data, and we would like to prepare this data for kinetic analysis. If we see viscosity, for example, shear viscosity, as it measured in linear scale, then we have two parts. The first is horizontal, before starting of reaction, and then very, very strong increasing during our curing, during our cross-linking. Here, for example, the viscosity changed the change of viscosity is very high. So viscosity change by several decades, here by 7 decades. So viscosity changed by 10 power to 7. It's really very, very high value. And therefore we have, it looks like a strong increasing line during the curing. And therefore it's really hard to make analysis for linear wise scale. We recalculate everything to logarithm, and then we see very nice line, very nice decreasing of baseline because of the reactant state, then increasing because of chemical reaction, and then the final part is our product. Again, we do not use linear scale, we use a logarithmic scale for shear viscosity. Second part is a baseline. Here we just have a screenshot from the software just to see the normal measured data. If the data are measured very well, then we have initial part for reactant baseline and final part for product baseline. And in this case, in the software, we should select tangential baseline. Then the software can calculate both baselines for reactant and products and remove it. So here, for measured data, we have both baselines, and after preparing data for kinetic analysis, we have initial and final parts. They are horizontal, and here we have for prepared data only information about chemical reaction, no any information about dependence of viscosity on temperature. Sometimes happens something like this if the data are not measured until to the end. It happens if sometimes if the settings of ariometers were not really good, were not really correct. But in this case, we see that the final measured point is still behind the inflection point. In this case, we still can make analysis of the data. We should select left tangential baseline, then only the left baseline will be calculated, and it is assumed that the product baseline is the same. So for measured data, we see the same reactant part, initial part for all measurements, and then we remove it and have horizontal part for initial, for prepared data. Now, just a couple of examples here. Here the data, I like this data because they are very understandable and well measured. The data are from our customer, SPM Composite, and they kindly allowed to show this for our sales meeting. This is B-stage prepreg epoxy system. And you see that the measurements are done with heating rates from 0.5 K per minute to 5 K per minute. And we are able to create one chemical reaction with autocatalysis, which can describe all this data. Here the points are experimental data, and the lines are our data for one kinetic model for all cores. So, and if this one kinetic model can describe everything, then we can use this kinetic model for predictions. For example, we can make predictions of conversion. We put a temperature profile into our software, heating, isotherm, and then cooling, and calculate conversion. Conversion is degree of cure. During heating, you see the green curve. During the heating happens nothing. During either term, we have curing, we have chemical reaction, and then happens nothing again. But if it's enough to no conversion, no. If somebody works really with curing of viscous materials, then, and do not take into account the viscosity, then it happens something like this. Some drops, some orange peel, some cracks, some non-uniform curing. And if you would like to avoid all these problems, then it's necessary, really necessary to know viscosity. We put the same temperature program, make another click, and we have a viscosity. You see the blue curve. Viscosity goes down during heating. It's a normal behavior of material without any chemical reaction. It's just a baseline for reactant. Then increasing because of a chemical reaction, because of curing, increasing during isotherm, and then increasing again during heating. This is the baseline of the product. Another example, it's just a normal glue, it's Araldit. You can buy it in any supermarket or somewhere on Amazon. And our colleagues, my colleagues from laboratory, make a measurement on our Kinexus, and we did analysis with Kinetics Neo. You see here 2 steps. And the first step of chemical reaction is really very fast. It's about 5 minutes. And after 5 minutes, the material goes from high viscous, from low viscous to high viscous, but you still can adjust the connected parts, and you just make some kind of moving after 5 minutes. But after next 24 hours, it is, we have a second step of reaction, and everything will be fixed. And after 24 hours, the chemical reaction, the curing is finished, and you cannot move your parts which are connected. So for Araldit, there is an application note which is done by Claire Strasser and will be soon in our knowledge base. And I would like to tell you that all actual information about Kinetics Neo is on our website, kineticsneo.com. And here we have user guide, training examples. Here everybody can get or request a trial version for 30 days. And this year we have very nice webinar for thermokinetics. You can get PDF and video on our website. And this webinar contains unique features of Kinetics Neo software. They are really unique features, the features which are not present for in any other thermokinetic software. So, and I think that information about these features are very important for you and for our customers. Thank you very much.